In amplitude modulation, the message signal is encoded directly into the height or amplitude of the carrier. This creates a specific vulnerability. When external noise interferes with the signal, it alters that amplitude, corrupting the data before it reaches the receiver. Angle modulation uses a different approach by maintaining a constant carrier amplitude, AC. Because the data is not stored in the wave's height, the receiver can ignore amplitude fluctuations caused by noise, preserving the original message. This immunity requires a trade-off. To protect the signal from noise, the system must occupy a wider range of the frequency spectrum, using more transmission bandwidth than standard AM. Engineers implement this by varying the angle of the carrier in one of two ways: phase modulation, or PM, and frequency modulation, or FM. By moving the data payload from the wave's amplitude to its angle, the system exchanges increased bandwidth for higher signal integrity. Every angle-modulated wave is defined by the equation S of t equals AC times the cosine of the instantaneous phase, theta I of t. For an unmodulated carrier, this phase is the sum of the carrier frequency components, 2 pi fct, and the initial phase offset, phi c. The physical frequency of the wave, Fi, is the rate of change of that instantaneous phase. Mathematically, it is the time derivative of the phase divided by 2 pi. This calculus relationship links PM and FM. While they appear to be different modulation methods, they are mathematically tied together through this derivative. To demonstrate this link, we can observe how both equations respond when we feed them the same linear input signal. Mapping these calculus derivatives onto physical waveforms reveals how abstract math dictates the actual behavior of communication signals. We will use a message signal, m of t, defined as a linear ramp. Starting at time 0, the voltage increases at a constant rate of 1 volt per second. In phase modulation, the instantaneous phase varies with this message signal, scaled by the phase sensitivity constant. As the voltage of the message increases, the phase of the carrier shifts accordingly. Since our input is a linear ramp, the added phase increases at a constant rate over time. Since frequency is the derivative of phase, constant phase change yields a fixed frequency shift. The middle graph's phase-modulated signal shifts to a higher, stable frequency. Its uniform wavelength is shorter than the unmodulated carrier, remaining unchanged as the ramp rises. Phase modulation transforms this steadily increasing voltage into a single static jump in frequency. Frequency modulation operates differently. Here, the instantaneous frequency, rather than the phase, varies linearly with the message signal, scaled by the frequency sensitivity, Kf. This creates a unique mathematical requirement. If we want the frequency to follow the message signal, the phase of the carrier must become the integral of that message. Applying our linear ramp to this integrated framework, we can compare the input to the frequency-modulated output. The integral of a linear ramp is a quadratic function, meaning the area under the curve grows quadratically over time. As this area accumulates, it forces the wave's frequency to change continuously. In the bottom graph, the wave begins to compress immediately, creating a chirp where the cycles become closer and closer together as voltage rises. Because frequency modulation relies entirely on integration, a simple linear input produces a wave that constantly and physically accelerates. Comparing these three graphs shows how the same linear input produces two different physical results based on the modulation type. The PM output stays at a fixed frequency because the slope of the input is constant, while the FM output frequency rises because it follows the value of the input directly. If we plot frequency over time, the difference is clear. PM creates a horizontal line, while FM creates a diagonal line matching our original message. These methods are variations of the same angular control, linked by calculus. In practice, an FM signal is effectively a PM signal, where the message has been integrated before reaching the modulator. Understanding these derivatives and integrals is necessary for designing the hardware that decodes these signals, allowing us to extract data from complex modulations. Whether the system uses phase or frequency, manipulating the mathematical argument of a cosine wave provides the primary safeguard against amplitude-based noise in modern telecommunications.